Okay, so welcome back. This is part 3 in our series where we show you how to convert your Arduino into an oscilloscope. And you can see we've developed this application here. And I've got a very simple connection to my Arduino where I've got from my signal or function generator coming into an analog pin on the Arduino. And it's converting that into data that we send over the USB to our computer. And the computer has an application that basically makes it an oscilloscope. And you can see the waveform coming in from the signal generator is a square wave, and it's updating fairly quickly, fraction of a second. And what we're going to do is we're going to show in the series how to develop this application and some of the things you need to know about the Arduino and oscilloscopes and some of the design criteria we're going to need. Now, in the previous videos, I encourage you very strongly to look at those two. The first one, we talked about the general design concepts and design criteria, and we developed a simple functional block diagram to show the functions we're going to need in order to make this work. And we also talked about some issues we're going to have to address. And in the previous video, we talked about one of those issues, which was how do you make this USB connection to the Arduino, the serial COM connection, how do you make it respond fast enough so the data coming in from the Arduino can be updated? Like I said, in this case, every fraction of a second, we're updating the display. So we're going to have to figure out how to make that serial port very fast. And we did that in the previous video. I encourage you to take a look at that. And we also talked in the previous videos about a couple big issues that we're going to need to address, and we're going to try and tackle those in this video. One of them was the limitations of the Arduino. And one of the big things we talked about was the memory limitations, the onboard memory. So for example, we're going to be grabbing, you can see here, I've got 200 milliseconds worth of data that's being continually updated. So that data has to be stored on the Arduino somehow before it's sent to the computer. So we talked about before how all of this data that's grabbed by the Arduino, this 200 milliseconds worth of data, or in this case 500 samples you can see over here, those 500 samples are being stored on the Arduino, and then they're being sent over the USB to the computer so it can process it and plot. So one of the limitations is how many samples, how much data can you store on the Arduino? What's the limitation? Can you store 1,000 samples? Can you store 2,000 samples? And we're going to take a look at that in this video. So here is kind of a discussion of some of the types of memory on the Arduino. We'll go through this fairly quickly. You can see flash memory, which is program space where you write your sketch. That stores the Arduino sketch. There's also static random access memory, which is SRAM. And that is where the sketch creates and manipulates the variables when it runs. So in other words, we're going to store those 500 samples in a big array, and it's going to be stored in SRAM or static RAM. So we're going to make sure we have enough SRAM space on the Arduino to store those 500 samples. So we're going to have to take a look at that, because if we don't have enough memory and we try and store a bunch of samples and we run out of RAM, we're going to get crashes and all kinds of problems. So that's why it's really, really important to, as I've said before, don't just start writing code, plan it out and see what you're going to need to make sure that you've got enough space and enough speed to make sure this is going to work. So SRAM is going to be a big factor. EEPROM is electrically erasable, programmable, read-only memory. Basically memory space that you can use to store long-term information. We're not going to have to worry about that right now. So flash memory and EEPROM are non-volatile. In other words, when you turn off the power to the Arduino, that memory is going to stay. Still going to have the flash memory where the Arduino sketch is stored, so that's going to remain, but any variables are going to be gone. So SRAM is volatile and it will be lost when the power is cycled. Now, the ATmega328P chip, which is found, this big chip right here, which is kind of the heart of the Uno, has the following amounts of memory. Flash is 32K bytes. SRAM is 2K bytes, or 2048 bytes of data. So this is going to be very important. Is 2048 bytes enough to store our 100 samples or 500 samples or however many samples? And EEPROM is 1K byte. So let's take a look at what our samples are going to look like so we know if we can fit it into the RAM. So again, there's not much RAM available to the Uno. It's easy to use it up by having lots of strings in your program, for example, or big arrays of data. So for example, a declaration like, if we have an array of characters or a string that looks like this, each number is going to take some memory, of course. This message, this array of characters, puts about 15 bytes into SRAM. Why is that? Well, each one of these characters takes 1 byte, and there's a terminator. So if you add all this together, it's something like 15 bytes for each line, each string, or each character array. So this is going to represent 1 sample. And if we have like 100 samples, you're going to multiply this 15 bytes by 100. So the total requirement is going to be about 1,500 bytes for 100 samples. It doesn't take long to get to the 2048. We just said, only 100 samples and you're up to 1,500 bytes. Here's 2048 is the limit. So, we have to worry about running out of SRAM even with our 100 samples. As you may notice, we're doing 500 samples. So how are we going to do 500 samples if 15 bytes per sample? If you do the math, 15 times 500 samples, that's already 7,500 bytes. But we've only got 2,000, so we're going to have to take a look at this and say, wait a minute, I can't fit 500 samples that look like this into RAM. I'm going to run out really quickly and the program's going to freeze. So we're going to have to figure out what we're going to do, how we're going to work on this. One thing you can use in the Arduino to determine the sizes of arrays and strings is to use the size of operators. So just keep that in mind. Some possible solutions in general for making sure you don't run out of SRAM. If your sketch talks to a program running on a desktop laptop, as we do, you can try shifting data or calculations to the computer, reducing the load on the Arduino, okay? We may want to consider that. Since we have a computer, maybe offload some stuff to the computer. Maybe not, but at least it's something to think of. If you have lookup tables or other large arrays, use the smallest data type necessary to store the values you need. For example, an int takes up 2 bytes, while a byte uses only 1. So we're going to have to start looking at some possible solutions to figure out how we can fit, in this case, our 500 samples into 2K of SRAM. So one solution, you might think, we've got a time and a value. Do we really need to store the time? Again, it's kind of a irrelevant microsecond value since the sketch started running, and it does give you good, accurate increments of time. So you take the time between 1 microsecond reading and the other, and that tells you how many microseconds between samples, for example. But can't we just generate that in our computer code? Can't we say, okay, we're going to assume that this starts at time 0 and we know what the sample rate's going to be, so why not just generate our own timing, okay, instead of using those values from the Arduino. For example, if you've got 1,500 bytes available in SRAM after you've got all your other variables, you can have about 700 samples if you work it right. So for example, 1,500 bytes by 2 bytes per sample. So if we only use 1 int instead of that, the microsecond value, we instead just store the 0 to 1023 value. 1,500 bytes over 2 bytes per sample means I can get like 750 samples. Maybe that will work. In practice, I found that like 500 samples is more reliable, but at least we now have a ballpark. We're going to say, well, we might, 500 or 700 samples is going to be our limit for storage in the Arduino. So we're going to have to make sure we consider that when we're developing our final Arduino code and our C# application. Okay, so now that we have a feel for what our challenge will be in terms of SRAM usage on the Arduino, and we're going to have to take a look at that and make sure we don't run out of RAM. And in the previous video, we looked here on our timing diagram, we looked at one way to make the USB baud rate much faster to speed up the response, and we got down to a very low value. So we're okay with the speed. What else could there be that we need to look at? Well, as we mentioned, I think in the first video, we intentionally left out one consideration when doing this timing chart, and that is going to be something that can have a very big effect on slowing down this response, even worse than a very slow USB. And that is this little task right here that the Arduino has to do when we send our string request. It has to read that string request and parse it to find out what does the computer want it to do. And in that little request, it can end up taking a very long time. What are we talking about? Well, there is a line that we have in our sketch that is the serial.read string, and it basically reads characters from the serial buffer into a string. And what you may not be aware of and can be causing a lot of problem is this function terminates if it times out. So it needs to wait until it's absolutely sure that it has retrieved the string that you sent it. If it's not sure that it's retrieved the full string, it's just going to sit there and time out and wait and wait and wait. And there is a parameter you can set called the set timeout, and it sets the maximum milliseconds to wait for serial data, and it defaults to 1000 milliseconds or 1 second. So in other words, if you don't do it right, your read string could take at least 1 second. If it's not sure it's got your entire string, it will wait for 1 second and then time out and then go on to the next step. So we have to be very careful when we're reading this string, that we make sure when we send the string, we got to make sure that this read string knows that the string is terminated, and so it can move on and not just sit there and time out. So what we're going to do is we're going to replace our read string with something that is much nicer, which is read string until, and we're going to tell it what the termination character that it should be looking for. And when it recognizes that /n termination, it's going to say, oh, okay, I don't need to time out anymore. I've got my full string. Let's go on to the next line. So this read string until reads characters from the serial buffer into a string. And when it sees this termination character, it knows it's done and it moves on. So very important that you make sure before you start writing code that you understand these things, so that you know you don't just do a read string, you got to do a read string until to make sure it recognizes the character. Here is our sketch, and you may notice that there is a warning message here that I put in the offending line. And when we are checking, we've got our setup and we've got our loop. It says if serial available, so it gets something on the in the input buffer, we do the receive string equals serial.read string. And this can cause a 1 second delay if you don't do it right. So, you know, we speeded up the USB port to really fast 3 millisecond response, but this is just going to sit there for a second until it's absolutely sure it's got the string. So we're going to need to change that to a read string until and give it the termination character so it will read this really quickly and then move on and determine does it start with a B and do all the work. Okay, so now that we've taken a look at the Arduino and some of its inherent limitations and its capabilities in terms of serial baud rate and how much time it takes to read a string and also how much memory it's got, let's step back a bit and see if there's any other issues we need to tackle. So looking at the scope here, you can see the basic operation is, in this case, we've got 200 milliseconds, and you can see that it takes a scan of 200 milliseconds, displays it, and then refreshes it and does another 200 milliseconds, okay? If we lower the time that it displays, here it's only 50 milliseconds, you can see it's displaying and updating, but it seems like it's going a lot quicker. So how do we do that? You're going to have to gather and display 50 milliseconds, and then there's going to be some time delay, and then you're going to do it again and again. And depending on how much time you have displayed, that's going to affect how often you refresh. Because, for example, if I've got, in this case, I've got 500 milliseconds or half a second, I'm going to have to wait for the Arduino. It's going to take half a second to gather this half a second of data. And we're going to have to process that and plot it. And then we're going to have to do it again. So depending on the user's selected scan rate, we're going to have to change how often we request the data. And we're probably, once we do a scan and a plot, we're probably going to want a little buffer time before we do the next one to make sure that we don't, as we said before, we don't want to start requesting data from the Arduino when it's busy doing the previous scan. So let's take a look at, go back to our timing diagram and see what we need to consider to make sure we don't have any problems. Okay, so I've modified the timing diagram to show not just the one scan that we showed, but the relationship to the subsequent scan. So I'm going to scan it once, have a little bit of a buffer in here, and then scan it again, and then a buffer and scan it again. And you can see here that there's a reason for this buffer. You don't want to start requesting data when, for example, the C# is busy doing some processing, or even worse, if the Arduino is still trying to process and send, you don't want to request data. You want to wait until you've got your scan, you've got it plotted, and then we're going to have a little retrace time. If you're familiar with the CRTs from way back when, they had what's called a flyback time, where you display the screen, the image on the screen, and then you give it time for the ray to go back to the top left and then start another scan. So it's kind of what we're doing here. We're trying to give it a delay or a buffer time before you start the next scan. So as you can see, we're going to have to start figuring out these times fairly exactly, because we don't want to give it too much buffer where we're sitting there, we don't need to. So we're going to have to figure out the times involved in all of these. And we already got a start on that in the previous videos, but it's going to be more important now. We're going to have to figure out what the different times are and what kind of buffer we're going to need, and what's the total scan time, including the buffer, so we know when to start the next request. The other thing we need to figure is, say we're grabbing a sine wave, and for example, let's say we've got 100 samples, and here's our 100 samples. And again, we said they've got about a 0.1 millisecond time required to do a sample. So that's why we've got these little sample blocks here. And you can see that there is a minimum amount of time you're going to need. For example, if you do 100 samples at 0.1 milliseconds per sample, you can't have a scan time, a total scan time of less than 100 times 0.1 or 10 milliseconds, or you won't get all your 100 samples done because they take 0.1 millisecond each. So we're going to have to be very aware of how many samples and how long they take, and we're not going to want to request a scan that is shorter than the possible time that it takes to do a scan. And the other thing we want to consider is maybe we don't want to do the scans as fast as possible. Maybe we want the user to say, hey, I want to see not just maybe 10 milliseconds, maybe I want to see 1 second's worth of data on the screen, and you refresh it every second. So maybe what we're going to have to do is, we've only got 100 samples, but it has to reflect 1 second, a 1 second scan. So what we're going to have to do is we're going to have to take each sample, do a sample, then a delay, then the next sample, so that fits into whatever the time scan period that the user wanted. So that's another thing we're going to have to think about. So here is kind of a diagram of what the scope is going to have to do, and some of the things we're going to have to determine. We saw before there's a total scan time for each refresh on the screen. So the user is going to say, hey, I want 100 milliseconds per scan on the screen. So we're going to have to determine that somehow. And then we're going to have to figure out what's the delay for each sample to fit all those available samples into what the user wants for a scan time. And we're going to have to know how many samples are available so we can figure all that out. And then we're going to have some buffer time to make sure we don't start a new scan too early, which means we're going to have to figure out what's the refresh time. So I send a request here. What's the refresh time when I send the next request for data? So we're going to have to get all these timing things figured out. We're going to need the time per scan, which is basically the time range displayed on the scope. The refresh timing, which is time between successive scans, which is this time. Number of available samples per scan, which is a memory limitation. And then the delay per sample to fit the available samples into the desired scan time. So very, very, very important, and yet another reason why you don't want to just start writing code. You're going to have to figure this out, and you're going to have to figure out where you're going to get this information and how you're going to fit it into your code. The way we're going to approach this is we're going to have the user set how much time per scan, basically the time range displayed on the scope. They're going to set the time per scan, and then the application can calculate the rest. So once you know this time per scan, and you know the number of samples that are limited by the memory, then all you have to do is divide the scan time by the number of samples, and you can figure out the delay, and you can figure out the total refresh time once you've measured all this stuff. So ideally, we'll just have the user say, give me 0.1 second scan time, and our application will calculate all the rest of that. But again, we're going to have to know what's the maximum samples we can use based on memory, and what's the refresh time after we've measured how long this actually takes. So as an example, let's say we've got 100 samples max per scan based on memory limitations, and we've got a 0.1 milliseconds required per sample with the analog read. That means to do 100 samples, we're going to need 10 milliseconds. Now, if the user says, I want a 0.1 second scan time, I want to see 0.1 seconds on the screen, or 100 milliseconds, we're going to need 100 minus 10 divided by 100, or 0.9 milliseconds delay per sample. 0.9 milliseconds delay plus the 0.1 is 1 millisecond, and 100 samples is 100 milliseconds. Now, what I've done just for information, I have checked the actual elapsed time with my application just to give you a feel. So if I said 100 samples, and I've asked for a 0.1 second burst duration or scan time, which is 100 milliseconds, the results I get are about 100 or 0.125 seconds total time to get everything accomplished. Now we asked for 100 milliseconds scan time, but it actually took 125 milliseconds. And then I've got a buffer included in this calculation, and it turns out to be 80 milliseconds. Actually, I asked for 100 milliseconds, but because this went over, it went from 100 milliseconds scan time to 125 milliseconds. It used 80 milliseconds of the buffer to give me a 200 millisecond total time. So I asked for 100 milliseconds display, but it actually takes me 200 milliseconds before I can ask for an update. So that's why it's important that you know how much buffer, so you've got a little room in there so you don't start overwriting. So what lessons have we learned? First of all, don't run out of SRAM on the Arduino. Do use the high-speed USB that we showed in the second video. Do use serial.read string until to make sure that your serial read doesn't sit there for a second doing nothing. Also, figure out the actual elapsed time for each part of the process. Again, very important, so you can get your buffer time and you can make sure you understand what's going on so you don't have any unknown crashes. And to do that, we showed in the first video how we've got this debug mode where you check a checkbox and it calculates the elapsed times for these different parts of the process. So it's going to be very important, especially in this, to have some sort of debug mode that shows you what's going on. And then again, we're going to have a buffer time between refreshes, this buffer time, and we're going to have to calculate what's the ideal buffer time. And then also we can't request a scan time that's less than 0.1 millisecond per sample. Okay, so in the next video, we're going to talk about some techniques we're going to use both on the Arduino side and in the C# code to measure performance and to do debugging and check the timing. For example, here we've got our debug checkbox where it puts out elapsed times for different functions that we're performing. Very, very important here so we can figure out what the final timing is going to be. So we'll talk about some of those techniques in the next video. And then after that, we'll start getting into the Arduino code and then the C# code. So if you like any of these videos, I appreciate it if you like and subscribe and hit the bell notifications. And most of all, please let others know that we're here so we can get some more viewers. Appreciate it. Otherwise, take care and have a really good day. Thanks.